Hello again, everybody. So I'm now going to talk to you about machine learning. This is an area, frankly, it's been around for many, many years, decades even, but has only really, from my point of view, become very exciting in the last couple of years because we've been able to take something that's been an academic topic and really put it to use for users and for developers. And I'm going to show you all of that with this upcoming presentation. So firstly, I guess I want to talk a little bit about machine learning at Google, because machine learning is an area that's like rapidly developing. And the cool thing about machine learning where it's at today is that you can start to use it in your apps without being a machine learning expert, or ML, I may use to shorten. Because what we've done is we've abstracted some of the work that we have done in machine learning, and we've provided that in high-level APIs. So if you know how to use an API, you can benefit from machine learning itself. If you, of course, want to go deeper and build your own models, train your own models, serve your own models, we offer something called Tensorflow. And I'm going to talk about that in a bit more detail. So let's look at how we use machine learning in Google products today to start with. And here's a quintessential example, right? We've got a number of images, and we're able to run our image recognition models against this. And so this particular model is called Inception. And you can go and grab Inception today. We've open sourced it all. It's available on GitHub. And when you grab Inception, what you'll find is there's a pre-trained model in there to recognize all of these different types of objects. And you'll see how advanced it's gotten, right? So on the left and the middle image there, what you're seeing are two different salamanders. But the model is able to actually distinguish between a spotted salamander and a fire salamander. On the right-hand side, you've got a dog, but we don't just stop at dog. We tell you that it's a retriever. We tell you what type of dog it is. So Inception, available now. You can go ahead and grab the pre-trained model and run it up against your own services if you have that kind of functionality. Now, many of you may have heard of something called Deep Blue, which was IBM's kind of supercomputer about 20 years ago, so around 1995. And Deep Blue became known for defeating the chess champion of the world in 1995. Now, the way it was able to do this was through brute force algorithms, because at that point, computing had got to a stage where it could walk the game tree faster than a human could think it, right? And that was 20 years ago. So if you fast forwarded to 2015 and looked at the game Go, and Go, by the way, has a much deeper game tree than chess does. The number of combinations and moves in Go are vastly more in number than chess. But fast forward 20 years of computing, and imagine all of the advances we've had in computing between 1995 and 2015. But in 2015, the best computer that could play Go, could only compete at an amateur level. That's as far, even in 20 years, we hadn't mastered Go. So it was a real shock to the machine learning community and even the Go community when earlier this year, Google's AlphaGo was able to defeat one of the best Go players in the world, Lisa Dole. And the difference between AlphaGo and solutions that had come before it is that it was running on our machine learning technology. AlphaGo is an ML-trained model based on thousands and thousands of Go games that have happened historically. And AlphaGo is able to basically apply ML concepts and walk that game tree much faster than what we've been able to do before it. Now, something that you may not know about AlphaGo is that the way that it plays the game is it just gets an image of the game board. It doesn't get told in digital inputs as to what the state of the game is. It visually sees what the game board looks like, parses that, works out the game state, and then starts to walk the game tree on what its next move should be. Now, image recognition can actually be quite cool, But if we take our machine learning technology, we can do some interesting things like create or generate images from scratch. So on the left-hand side, you've got a photo there of the UN United Nations building. And in the middle here, we've got Picasso. Now, Picasso had a specific kind of style of doing his art. So what if we applied our ML techniques to go recreate that photograph on the left in the style of Picasso? Well, you could end up with something like this. Now, here's another model that we've trained and built. And again, we've open sourced this. You can go to GitHub and go grab the code for specifically this model and use it to take your photos and apply different photos, like the style of those images, to the source photo as well and recreate it from scratch. But what if we took away the concept of style? What if we were to go one step further and say, hey, you know what? I'm going to give the machine, I'm going to show it an image and then tell it to recreate that image just using our ML models. And we did that experiment with something called Daydream. It looks pretty trippy, actually, if you ask me. But it creates fascinating digital art, that this is how computers see things. And you start to see kind of recursive patterns of things, of elements in these images that are being used to create other images. I think it's pretty cool. But then why don't we look at a more practical example of natural language processing, right? Here is the world's most accurate parser in action. And again, we've open sourced it. Does anybody know what this is called, our text parser, natural language processor? It's called Parsi McParsface. That's what happens when you let engineers name your products. So Parsi McParsface, it's hard to say, can analyze sentences and tell you things like what is the direct object that the sentence is referring to, what is the request. And you can see how we're using this all throughout this sort of technology throughout our products. In fact, let me show you right now. I use Google Play Music every day. This is where I use to listen to my music. And this is a home screen that's slightly out of date because just last week we updated the app with a new home screen. But the technology powering it, the ML technology powering this is the same. The recommendations that you see here on the home screen that says, hey, would you like to listen to this kind of music? It's based on a machine learning model. It's able to understand your tastes in music, your moods, your activities, the times of day, right? And recommend playlists that suit for you. It's entirely personalized. In Gmail, we use machine learning to recognize spam, right? So we're continuously getting better. As spammers get better at spamming us, Gmail continues to get better, and we use machine learning to identify this spam. In Google Photos, when you do a search, and here are actually some photos of cherry blossoms that a colleague took in Japan, that colleague did not tag any of these photos. When you take a photo, you upload it to Google Photos, it's able to go and recognize the objects in your photos and annotate them accordingly so that when you do a search, you can do a search by name, by the type of object it is, and it will return those photos. It's really cool, actually. I've got pictures of my kids, from their various birthdays, and you can search for cake, and you start to see all the photos of their birthday cakes come through. I never went and tagged any of those. We use ML models in speech recognition, right? When you say, I won't say it because everyone's phones are going to go off, but when you call on Google Assistant or Google Now, and in fact, if you've got the Google Home products, you notice that we're doing a lot of speech recognition there. And we're going beyond just question and answer. We're able to keep context. You can say, how old is Barack Obama? And then you can follow up with, how tall is he? And it knows that the he you're referring to is the same he, or Barack Obama in this case, from the previous question. This is my favorite example. It's actually Google Translate, and you can point it at actual signs. And I just want to break down the complexity of what's happening here. So we have a sign. We're telling Google Translate to use the camera. It's recognizing the text. It's then translating that text into whichever language is what you want it translated to. And for me, the most impressive part is that it's actually substituting it back into the image in real time, right? Or near real time. Maybe it's not 30 frames per second, but very close. That's pretty awesome. I also am an inbox user, and when you use inbox, when you go to replies, across the bottom, I'll let the animation occur again, but across the bottom you get these auto responses. And again, those auto responses are generated using a machine learning model. They're personalized to you. So one, it looks at the context of the conversation, but two, it tries to talk the way you talk. So all of these machine learning models, we've spread them throughout our Google products where we can delight our users. And they use a specific type of machine learning called deep learning. And up until recently, deep learning was used primarily for academic purposes. But what we've been able to see is over the last few years, as we've integrated these techniques into our products, deep learning is no longer just an academic field. It is something that's delighting users every day and at scale. So that sort of sums up a little bit about machine learning in terms of some of the libraries that we have, as well as how we use it in our consumer products. Let's talk about development. I'm not a machine learning expert, but I understand exactly what's going on here, and I can use this because we have made APIs available for developers. So I'm going to talk about some of these. Because the cool thing about these is, as long as you can use an API, you can benefit from a machine learning model. The Mobile Vision API allows you to recognize objects. But this model, when you use this API, is available entirely offline. So your app no longer needs to hit a server to actually go and benefit from this. And we have a few specializations in this API. We've got the Face API, the Barcode API, as well as the Text API that you saw in the Translate example. And so we're going to work through an example here, all right? We're going to have this photo, and we're going to replace her eyes with googly eyes, right? And I'm going to show you how simple it is to do this. It's just a few steps in terms of code. And I'm sorry, I'm not sure how clear it is, so let me walk you through it. We're going to do it in 3 steps. Step 1 is we're going to create a face detector, right? And what we say is it's literally 1 line of code to initialize this. What we're going to say is that the landmarks, the features that we want to find on a face, we want all of them, right? So whether it's eyes, nose, mouth, whatever it can find, let it find it. So we create one of our face detectors. And then that second step, that second box here, 1 line, that's where the magic happens. Where we just say, hey, detector, that thing we initialized, here's the image. Go ahead and find those landmarks. And it comes back to us in an array. Now, step 3 is us just iterating through that. And one thing I want to call out is that first for loop, that outer for loop, we're actually iterating faces. In other words, this API recognizes multiple faces. And then for each of those faces, it can give you the landmarks. And so the inner for loop is, give me all the landmarks, and then you can say, give me the eyes, and get pixel coordinates for that. And then you substitute it with the image that we put in there. So all of this code, we just ran a really comprehensive machine learned and trained model. We didn't have to learn any machine learning to do it. We just benefited from that pre-trained model. You don't always want to do things just on the client side, though. You probably want to serve your users at scale, do things in large batches. So for example, if you have some user-generated content where users can upload their content to your backend, we've added a number of capabilities on the Google Cloud Platform, number of APIs that enable you to serve it at scale. They are speech, vision, and translation. We also have a specific set of APIs and infrastructure coming called machine learning. And what this is going to allow you to do is train your own models, serve those models, and basically use it all throughout your backend infrastructure if you want. Now, the types of capabilities that you can have on the Google Cloud Platform are obviously greater than what you can do on your phone. We've got labels, faces, optical character recognition. If you're doing user-generated content, the explicit content detection is kind of critical because the internet can be a bad place. But we can recognize things like landmarks and logos as well, that this is the Eiffel Tower as opposed to this is just a building. Again, you can use these APIs without actually being an expert in machine learning. Pretty awesome. I now want to switch topics to TensorFlow. TensorFlow is already the most popular machine learning library in that first year, within a year, on GitHub. It's an open source machine learning framework that's available to you. And what you can do with TensorFlow is use the existing models that come with it or are shared by the community. You can train your own, you can develop your own models, and you can serve them as well. The other nice thing that TensorFlow does is it helps you learn machine learning. If this is an area that you want to get into, you can do so. Something that makes TensorFlow unique is that it is being used by researchers to build new models at the same time as being used in production at scale to just deliver existing pre-trained models. So it's got a multifaceted feature set and appeals to everybody, really. So we're going to work through a quick example of what it's like to do the equivalent of a Hello World application in TensorFlow. Now we're going to use Python to write this code, but don't worry, I'm going to walk you and talk you through it. So if you're not familiar with Python, don't be too worried. TensorFlow was designed with mobile and embedded platforms in mind, and I'll talk a little bit about that a little bit later as well. Our little Hello World type example is digit recognition. Right? We're going to be able to recognize the numbers 0 to 9. And this is kind of a classic machine learning problem that's used to learn this sort of stuff. So as humans, we actually take vision for granted. We're really good at recognizing digits, even though they're not very accurate. But when we look at it from the computer's point of view, when somebody writes a digit in a box, and in this case we've got 28 by 28 pixels, one of the ways that the computer sees this is that where the pixels are for the digit, we have weights. So a weight of 1.0 means it's a very black, dark pixel, and a weight of 0 is that it's white. There's nothing on here. And you've got gradations in between. Right? So it's a floating point value between 0 and 1. Now because it's 28 by 28 pixels, we basically have 784 pixels. And if I asked you, hey, can you do some digit recognition and solve it by hand, and you had to write the code, it'd be really, really hard, right? Because my digits don't look the same as your digits. Some of us have very perfect cursive writing. Others are like that number 1 you saw where it's kind of leant over a little bit. If you look at this letter 8, the bottom half of the letter is a little bit smaller than the top half, and other folks might write it a different way. So doing this as a series of if statements would be a nightmare. It would be crazy. It would be really ugly code and probably still not very dependable. And this is where machine learning helps us. So the way we're going to solve this problem is that what we need is a whole bunch of data, right? We need data to train it, and we need data to verify it. So we're going to take the MNIST database, which contains 60,000 images of digits, just handwritten digits. There's 60,000 of them in this data set. And what we're going to do with those 60,000 is we're going to split them up. We're going to use the majority of those images to train the model so that it starts to recognize these digits, and then we're going to use a different set to go and verify them. Your training set and your test set should never be the same, because otherwise you're not proving anything, right? So what we're going to do is select a statistical model on the way to learn this. It's called a classifier. And what we'll do is we'll take that training data, which is an input image. There's 28 by 28 pixel bitmap. We're going to pass it through our model, and we'll get a prediction as to whether it's which one of these digits it is. And then with the test data, we're going to input each of those digits through our trained model, and it's going to tell us this is what it thinks it is. And at the end of the day, we're going to have 6 lines of Python. 6 lines of Python gives us the solution for it. And I'm going to walk you through what these 6 lines do. So the first thing we'll do is go ahead and import the TensorFlow library package. And then we're going to load this MNIST dataset. That's the thing that contains those 60,000 images that I said. And in MNIST, basically, for that dataset, you're going to have the individual images, and for each image, you're going to have a value that says, well, this is the answer, this is the right value. We call it a label here. And then what we're going to do is we're going to use this thing called a linear classifier. And what the linear classifier does is it takes that 28 by 28 image, and it just flattens it. So instead of a 2-dimensional array, we end up with a single-dimensional array of 784 images. Of pixels, not images. So for each image, we're going to end up with 784 pixels. And then we have our output nodes. And these output nodes basically tell us which digit it is, right? It's the label at the end of the day. And the way that it works internally is that it creates these connective nodes. For each of the pixels, it says for that particular pixel, it'll have a node that connects to each of these letters. And you'll see how this works in a second. We end up with these weights, and these weights are really important. This is really where the model comes together. It says for this pixel, this particular pixel, we're going to assign a weight for each of these numbers. And so the higher the weight, the more likely that it's that digit. And we're going to do that sort of thing for every one of the nodes. So you end up with this many-to-many relationship. We've hidden the weights here because it's kind of hard to parse it. But what you can see is that for each node, we will end up with a weight. And so for each pixel, we will know whether it's what's our confidence level for that particular digit. Then what we're going to do is sum it up. So we're going to take the input value, multiply it across with the weight, and then sum it up, and then whatever's the sort of highest value, that's where we get to with which number we think it is. Okay, so what happens now? So we've got the linear classifier here, which we just did. Now what we're going to do is actually go ahead and train our data. So you see this? We say classifier.fit, and we're providing 2 values. One is the training data, right, the images. They're both the training data, sorry. One is the images, one's the label. So for the first element, it might be the letter 8, and the label will say digit 8. For the second, so on, and it just pairs those 2. And the way that it works inside about how to work this thing out, I'm going to describe what we're seeing here. It basically, the model starts off with kind of random weights. This is that like kind of peak red point you get here. And the way that it trains this model is that it uses those random weights, looks at the value, looks at the sum of those weights that we saw, and it says, oh, I got the number 6. And number 6 is actually wrong in this case because it might have been, let's say that first digit that we're training is the number 8. So it changes the weights, and then it checks, okay, now what was my result? And it keeps changing the weights. And every time it changes the weights, it looks at how far it goes from red, from that error range, to the positive range, where it's actually getting more and more accurate. So it keeps tweaking the values. Anytime its accuracy gets worse, it tweaks the values in the other way, right, in a different way, and then it improves its accuracy. And it keeps doing this across our whole data set. So this was our starting point. This was our error rate. And by doing this and getting our error down to as close to 0 as possible, we're able to come up with a more accurate model. This method of solving it is called back propagation, where we actually start with a certain error value, and as we change our model, if our error value gets worse, we change the weight in the opposite direction, and then we check our accuracy. So that's it. Once we've now done that whole classifier.fit, we can now go and check our accuracy score. So now what we're going to do is we now have a model that we trained. We're then going to now pass in the test data, the labels and the images, which is our test data here. Right? So remember we had 2 sets of data. One was to train it, one was to go verify it. This is what we're going to do. We're going to verify the labels using the classifier that we trained earlier, and we're going to predict it against the images that we had. And it's going to get a value. It's going to say, okay, for this image, I think it's the letter 8. For that image, I think it's the letter 6. It will compare it against the labels, and that metrics.accuracy score will compare those two arrays, and it will tell us what is our accuracy rate. Okay? And in this case, our accuracy for that MNIST data is 92%. So who thinks that's a good result? Who thinks that's a bad result? Why is it a bad result? You're saying image recognition is better. Sure, but for 6 lines of code, you'd still have to check it. Exactly right. If you had a system that was using this image recognition to find people based on their speed, if you're giving speeding tickets with this model, you're giving 8% of the time you're giving speeding tickets to the wrong person. So that's not very good. But for 6 lines of code, it's really impressive. What we can do is change one of our lines of code and make it 99% accurate. Where we use the linear classifier, we can use something called a deep neural network. And the way that this is different is that instead of having one set of output nodes that we have here, we have this like tiering system of various output nodes, and it's tiered in various levels. I'm not going to go through the worked example of how the deep network works because it does get quite complicated. But if you want to learn more about how to do this yourself, we have a Udacity course called Deep Learning, actually, and it's free, and you can go ahead and check it out at udacity.com. But the point is that it's this sort of network that gives us the type of results that we've been seeing across the products that I showed you earlier. For someone like myself who isn't a trained machine learning expert and where I would find it challenging to build one of these models, those APIs work perfectly. Right? Someone else has done the work, I can benefit from it. So that's how I like to think of machine learning. It's a developing area, and you can dive in either at the deep end with Tensorflow, or you can dive in at the shallow end with APIs, and you can still have a good swim, right? It's still a great experience, and your users benefit from it. I mentioned earlier that Tensorflow was designed to be available across multiple platforms. So actually, Tensorflow, we have mobile Tensorflow, and you can train and serve TensorFlow models on Android, iOS, and even Raspberry Pi. So if you want to go ahead and start to train your various apps and services, it's a good place to get started. So that's TensorFlow. Vibrant developer community, and it's a great, it's really a developing field. It's been around for a long time, but it's really accelerating. So if you want to dive in, check out tensorflow.org. We've got a couple of tutorials there that I do recommend for you. So one of the first one is MNIST for beginners, and MNIST was the name of that database we used. So we have MNIST for beginners, MNIST for experts, and then there's a separate tutorial called TensorFlow Learn Quick Start, which is where we walk through this Hello World example that we did, and they do go into the deep neural network and so on. Now, I was originally going to stop here, but I have some extra time, so is anyone interested in sort of learning a little bit about some more forward-looking technology that we've got? Okay, sounds like there is. So let's do a bit of a bonus round. I'm going to cover 2 additional pieces of technology, and the first one is Tango. Tango lets you see more of your world. What you're able to do is hold up your phone or your tablet, and you're able to watch as virtual objects and information appear on top of that real world, right? So basically, you're able to provide a richer and deeper experience for users to engage with. Now, for those of you that were here at DevFest last year, there was a talk on Tango. So the difference between Tango in the last 12 months is that it's graduated from Project Tango, which was something that we were researching, to products that are actually available in the market today. But before we get too far down that line, let me give you a few more examples of the types of things that you can do with Tango. You're able to bring virtual objects into, whoops, didn't click, there we are. You're able to bring like virtual objects into your world. So you'll see now this doesn't quite give it away because it looks like we've got a photo with a 3D model built on top. But this is a real 3D space. And so if there was a little creature down here, a virtual toy or pet, I'd be able to walk around it, on top of it, under it, and see it fully modeled in 3D in the environment around me. That's a bit of fun, but for more work type things, you can use it to model, to measure surroundings with 3D tools. So IKEA potentially could find this as useful to sell furniture to customers so that they could see how different styles of furniture fit in their place, both in terms of size and measurement, but also color. You can also use it to navigate stores and museums, show things like indoor locations, annotations like prices, product descriptions, and so on, as users are actually perusing through that space. Now, remember earlier I said that this is no longer a research project. We have products out there. The first device to ship with Tango is a phone by Lenovo called the Fab 2 Pro, and they shipped this about a month ago. I don't believe it's out here in Australia yet, but it is shipping in several parts of the world. So Tango is quite an exciting space for us because it's taking the real world and starting to annotate it. If you've got one of these devices, you'll find that there's already a bunch of work that developers have done. They've shipped applications that have a bunch of compelling use cases. And you can get started if you want with your own Tango projects because we provide the SDK at developers.google.com/Tango. So that's Tango, and that's really talking about the real world. I'm going to shift gears and start to talk about virtual reality. So Daydream is our new virtual reality platform. And what we want to do is take the work that we did with Google Cardboard and provide high quality virtual reality to everyone. We want to democratize virtual reality so that you can have great high quality experiences just with a device that's in your pocket. But let me rewind back to where this journey started, and it was with Cardboard. A couple of years ago, 2 years ago, at Google I/O, we went and handed out, just at the end of the keynote, one of our VPs sort of made an announcement that, oh, by the way, make sure you grab this piece of cardboard on your way out. And it was quite interesting to see because we didn't really elaborate much further beyond that. And so there were these folded up pieces of cardboard, and developers sort of started to unwrap them. There were instructions on how to put it together. And then at the end, it sort of said, oh, put your phone here. And that's all we said. There was a barcode to go and get the app and so on. And suddenly what people were able to realize is that you can provide some really great experiences with existing handsets. And so Cardboard really is being built for bite-sized VR experiences. And they work with almost any smartphone, whether it's Android or iOS. My personal favorite example is one that I'm going to describe. I've got young kids, and I remember when I was a kid, and I'm still interested in this, I used to always be really fascinated with Egypt and pyramids. And the way I'd be able to learn more about this is go to the library, like physically go to the library. Yeah, I used to do that. And go check out things like encyclopedias or books on Egypt, and you would have maybe a handful of photos that you could see and a whole bunch of text. For children today, with programs like Expeditions, in classrooms, they can don their Google Cardboard, and some of you have received Google Cardboard today in your swag bags. They could just don it, and through things like Street View, they can see what it's like to be at the pyramids. They can get a real sense of scale for how large these structures are. They can walk around it. They can walk through it. And I think that's just amazing that the type of experience that the next generation is able to have with technology such as this, it's really going to up the level of just how knowledgeable this generation is by the time they finish school. So I'm personally very excited about what Cardboard has been able to achieve. With Daydream, we've built a platform that's focused on high-quality mobile virtual reality. And Daydream is a platform for VR that is included, that's part of Android N, Android 7.0 Nougat. And it's really a spec that hardware devices need to meet in order to be considered a Daydream-ready device. So Daydream really provides very rich and immersive 3D experiences. And for those of you with Google Pixels, you can get that Daydream experience today because one, this device is already Daydream certified. And in Australia, we're fortunate enough that Daydream headsets are readily available. Let me just show you a little bit about what Daydream as a spec is. It's that hardware standard that I referred to, that new handsets or high-quality handsets must meet a set of specifications in order to be considered Daydream ready. Then we've built a reference design, and that's what the Google Daydream View headset is. It's a comfortable sort of cloth-based headset, fits nicely and snugly around your head. And then we've also produced a reference design for a remote so that users have a way of interacting with this virtual reality around them. The cool thing about this remote is it's like an extension of your own arm. So if you haven't actually had a chance, I believe you can get like product demos at Telstra shops and JB Hi-Fi. It's probably worth going and having a look. I was really amazed by when I did it, at just how tangible the whole world seemed and just how much of an extension of my own arms it felt like. That little circle across the top is a touchpad, so you can get swipe gestures. It's also quite clickable, and the buttons below it help you navigate through the system. So you've got the home button, you've got the back button as well. The cool thing about Daydream is that it isn't just going to be limited to the Pixel devices. We're working with a whole bunch of manufacturers to bring Daydream-ready devices to market. So this is an area that's going to explode very quickly as more and more devices hit the market. Again, the cool thing is, in terms of development, you can get started right away. One, we have retail devices available, but two, the SDK is available both for Android Studio and Unity. So in Unity, we've made it nice and easy that if you've got some interesting 3D experiences, you can check a few boxes, change a few configuration options, and start to play around with your apps and games in Daydream. So I'm going to leave it with that today. We've covered machine learning. We've covered TensorFlow. We've covered machine learning and TensorFlow. We've covered Tango, and we've covered Daydream. I think these sets of technologies are really, I said forward-looking, but really they're the present now. These devices are now starting to come out. Users are starting to experience them. And particularly with machine learning, we've already seen some of the magic that we can provide users with today. And it's really worth your time as developers to think about how you can benefit from these pre-trained models in your own apps to delight and provide magical experiences for your users. So with that, thank you very much. Yes? No, it's not. You can serve it, I think, in Go as well. Yeah. So the APIs that I mentioned for the higher level abstraction, they are definitely available in Java. In terms of TensorFlow itself, at the end of the day, it's an open source framework, and so you're going to start to see it come to other languages, if not by Google, then by the community. It's there for the world to see, but we needed a starting point, and Python served a really good point for that. Sorry, Andy.
No, I've got a mic, so...
Oh, okay. There's one over there. There's a question in this back.
Python has...
Yep, sorry.
Python has multiple libraries for deep learning or machine learning. Just wondering, TensorFlow can be useful for the basic developers, but how well do you have any analytics, how well it is as compared to other libraries like Theona and other ones?
I don't off the top of my head, but I know that there's been a lot of research into this field. It's a rapidly developing field, so any comparisons that you see today will probably be outdated very quickly. With that said, you're absolutely right. There's a number of vibrant machine learning communities and libraries out there. So I would say pick what works for you and get started from here. I've specifically spoken about TensorFlow. because it's what we build and it served us particularly well. I can't really speak to the other libraries, but you should basically look at each of those tools on their own merits and see what serves you best. I would also say that because it's developing right now, because there's so much enthusiasm in the field, my recommendation will be focus on libraries that have good communities, like active communities around them, because then they will probably evolve just as these technologies do as well.
So the example you talked about, Google Play Music, to give recommendations based on customized for a particular user, is the model trained by the particular user or generic model for everyone? Or how do we like?
It's a bit of both, actually. So we definitely look at your preferences. So typically you can get all sorts of signals from users. Signals like whether they're thumbing up or down is the obvious one. But hey, are you skipping a song, a specific song or a type of song all the time? How often do you listen to certain types of music? What time of the day? Maybe you listen to classical music as well as like heavy metal, and maybe heavy metal is your evening listen, and classical music is your morning listen. So it's able to discern these sorts of patterns. It starts looking for them. So yeah, there is generic stuff like, hey, this is considered like a certain style of pop music, or this is considered a certain style of grunge music. But then it can tailor to your tastes above and beyond that.
First of all, thank you for your explanation on deep learning. Very good. Just a little bit on if you set up your own models, how do you set it up in the API so you can use it? Can you go a little bit further on that?
Yeah, so the APIs are built against the model that they ship with. If you have your own models that you train, you need to put that API layer on top. The APIs that I showed you, like the mobile vision API, it's got its own model there. You can't substitute it with a different model. No, the way it's packaged is just like, hey, you have a single entry point. If you want to go deeper, I don't think so let me put it this way. If you've built a model, putting an API layer on top is like one of the easiest parts of that process. So the mobile vision APIs are for folks that aren't ML experts. For those folks that are training and serving their own models, building an API around that is reasonably easy compared to the rest of what you're doing.
Hi Ankur, this is Amey here.
Hi.
I have got a question on ML, that how quickly can it train itself, like the pre-built models, if you have a significant big training set, it has its accumulated weightage as you discussed, but how quickly can it adapt to the new inputs and give us a personalized suggestions or something like that?
Yeah, this is not an easy question to answer because it depends on what problem you're solving. We did a very simple hello world example. It only had 60,000 images. You're going to crunch through that very quickly. But in a real world production system, something like at the scale of Google Photos, you're not going to train it from scratch in seconds or minutes, right? It's going to take a while. So it depends on what it is you're modeling, how big your data set is, and frankly, with machine learning, the bigger your data set, the more accurate the bigger your training data set, the more accurate your model is going to be over time. So there isn't a quick it's like when somebody comes to you and says, hey, how long are you going to take to build a new app? Well, you're like, well, what does your app do? What functionality do you have? What platforms do you support? So on and so forth. So not a straightforward answer there, but it depends. In general, you want to have as big a training data set as possible there. Last question.
Hey, Lachlan here. Just around if you're doing TensorFlow on the device, in terms of if you just wrote a single TensorFlow, is there any capability of determining how performant a device is, and maybe if you don't care too much about 100% accuracy, that there's some degree of degradation around what it does, or do you have to create multiple profiles potentially?
That's a good question. Again, not an easy answer. In general, when you build any app, you make certain assumptions around the capabilities of those devices, depending on what your model is doing. If it's only recognizing 28 by 28 pixel images, you'll be fine. But if it's doing something with 12 megapixel photos that you take and recognizing those and doing something special with those, it'll be longer. So I would probably suggest that in terms of degradations, you probably would have different models. So in the Hello World example, we saw the linear classifier versus the deep neural network classifier. Clearly the DNN classifier is going to be heavier. So it really depends on sort of your domain and what you're trying to achieve. But it's something to consider. What I'd say is probably TensorFlow on mobile, you're better off using it for serving rather than serving pre-trained models, rather than using it solely to train the model from the get-go, because it is a mobile device. People really value their batteries. So training on like large data sets on a mobile device, unless there's something specific that you're doing that you can only get data that you can capture on the mobile device. And even then what you could do is capture that data on the mobile device and send it to your backend infrastructure to process. In terms of the performance characteristics of served models, it really depends on your domain.